All right, so if you're seeing my screen, you see the limit as x approaches positive infinity and negative infinity. It's actually two questions here, but it's the same answer. So we'll just look at it first from positive infinity. So this is one of those, because the degree is the same in both the numerator and the denominator, it goes to the horizontal asymptote, which is y equals 2/5. You learned that last year. So the answer is just 2/5. And then there's work that we can do if needed. But I think you said you don't need that for these.
To do what?
To show work to get this answer, or is it okay just
to no, if it just, yeah, if it has the same
okay. So now the reason that at negative infinity it's the same is because it's an even exponent. So the squareds, like if you put a negative number in for squared, you get positive and positive. If it was cubed, let's just say it was cubed, for example, you would get negative and negative, and it cancels. So it doesn't really matter whether it's even or odd. It really comes down to these right here. So it's still 2/5. So that this thing always holds, this horizontal asymptote, because it works for both directions.
Okay.
All right, so let's see if I can get here's the chat. Okay, so next problem is number 10. I can always do a related problem if needed. All right, so it says the limit as x approaches 0, e to the x sine x. So this is the limit as x approaches 0, e to the x times the limit as x approaches 0, sine x. And we always talk about the very first strategy is you always just put the number in. So this is e to the 0 times sine 0. And this is 0. So it doesn't really matter what this is. It always becomes 0.
Okay.
All right. 13.
So for the first one you did, you said it was like two separate problems because it's negative and positive infinity, but they're both 2/5.
Yeah, they're both 2/5. The answer is the same for both. Okay. And I get, it was just odd. Like normally they wouldn't do plus and minus infinity like that.
But like there wasn't any like difference in solving them, right? Or
no, not for this one. Like there are with certain problems, but not with polynomials.
Okay.
All right. So here, we've got kind of the same potential issue as previous from. Like you could break this up, x to infinity e to the minus x, limit x to infinity cosine x. The problem with well, this actually does work. There's also an alternative way to do it. Cosine, as you know, it just goes between 1 and -1.
Mm-hmm.
So this one you can think, okay, it's always -1 to 1. Well, what happens over here? E to the minus x, when you graph it, it looks like that. So it goes to 0. And 0 times anything is
0.
Now, alternatively, you can do a bit of manipulation with these. E to the minus x is equal to 1 over e to the x. So this can be rewritten as limit as x goes to infinity cosine x over e to the x.
Okay.
And then it's the same process. You do the limit as x goes to infinity cosine x, limit as x goes to infinity e to the x.
So either one works.
Yeah.
Okay. Okay.
And then you get the same problem. This is bounded from -1 to 1, and this goes to infinity. So it's a number over infinity, which is 0.
Okay.
All right, so 14 is the next one here. 14 is Okay, so this is the next one. This is the next one here, x plus sine x over x plus cosine x. So the idea with this problem is that this is really what's important, is the leading term here. Because at infinity, like let's just say you got really far out, sine x and cosine x, it's either like adding 1 or adding -1. But at infinity, that doesn't really matter. If you add 1 to infinity or subtract 1 from infinity, it's still infinity. So in short, you can say, oh, this is really like the limit as x goes to infinity, x over x, which is the limit as x goes to infinity of 1, which is just 1. But there's a bit of like, almost like a written part of this where you have to go ahead. Sorry.
What about the sine x and the cosine x?
Well, that's what I meant. These right here, plus sine x or minus sine x, plus cosine x minus x. What happens is that if you're at infinity, you just add 1 or subtract 1, so they don't even count.
Oh, I see. It's like insignificant.
Yes, exactly.
Okay.
All right, can we move on to 25 now?
Yeah.
Okay. All right. Cancel. Let me get this in view here. All right, let's snip that in. This is a good one. It's got some like left and right limits stuff. So let's take a look here. All right, so the first one is the limit as x approaches 3 from the left. So here's 3, and then from the left. So from the left, you're tracing down this way.
Yeah.
And it's always the y values. It's like, what is the y value as you come from this direction?
1.
Yeah, the limit as x approaches 3 from the left, g of x equals 1.
And then g of 3 is 1.5.
Yes, exactly. G of 3 equals 1.5.
Okay.
Okay. Determine whether the function is continuous at 3. The problem is well, let me show you where it's continuous. It's continuous everywhere except 3, because everywhere you can draw it without lifting up your pencil. There's
Because
nothing
there's
to
an
the
open circle, right?
it's more than that though, because there's nothing over here.
Oh, it just ends.
Yeah, it just ends. So the answer is no, because it ends. But furthermore, let's just say there was another thing here. It still isn't continuous because you have to lift up your pencil. And there's definition of limits also.
You need to say like the definition of the limit.
I don't know. I mean, like to me you do, but it's the limit as x approaches 3 from the left. G of x has to equal the limit as x approaches 3 from the right. G of x has to equal g of 3. This is needed for continuity.
Oh, okay.
And what that says, that's very mathy. It says that it has to approach the same value and the value has to exist there.
Okay.
And sometimes instructors want that for this. Okay, so part D is the points of discontinuity. Generally, this is where it's like, it's not really instructor specific, but for it to be continuous, it has to be it's an interval. And let me just give you the answers. We work backwards. From -1 to 3, this thing is continuous. It's not continuous at this point here, as far as my understanding is, which doesn't help you on the exam, but like at an endpoint, it can't be continuous because you can't get both the left and the right behavior.
Well, wouldn't it also be discontinuous at 3, 1?
Well, no, this is I'm sorry, this is an interval. This means from x equals -1 to x equals 3. It's not a point. It's this window. It's continuous, but not on those points.
So when they say the point of discontinuity, though, what did you put? Anywhere outside of that interval?
It's written kind of strangely. I mean, the answer it's looking for, I think, is 3 comma 1.5. I mean, that's probably what it's looking for.
Okay, well, wouldn't it be but 3, 1.5 has a closed circle. So wouldn't it be 3, 1? That is the discontinuous part?
Oh, I'm sorry. 3, 1. Yes,
Okay.
3, 1, 3, 1. Yeah, it's this point there that's discontinuous.
Okay.
All right, so part E, what they're really asking here, what they're really trying to get you to see is that the only removable discontinuities are holes. Holes are the only ones that you can remove.
Right. Okay.
So if you could fill in that hole, then you have a continuous function.
So if so there are holes in this. So
yes, the hole is there at 3 comma 1. There's a hole at 3 comma 1.
What do you mean by describe the new function?
It just maybe it means that it's you could say that it's continuous from -1 to 3 now.
Okay.
Rather than there being a hole.
Okay. So the hole is a removable discontinuity.
Yeah, and it's the only one. Holes are the only ones that are removable.
Got it.
All right, so I think that takes us to 29.
Yeah.
29 is kind of like one of the problems we saw on your maybe it was your Pearson.
Yeah.
Okay. Find the right hand and left hand limits at these 3 points. So it's A is really 3 questions. So it's find the left hand limit and right hand limit at x equals -1. Okay, so for -1, we're going to use this block here. So the top ones, yeah.
Because that includes -1. Okay.
Yeah. So the limit as x approaches -1 from the left, f of x, equals, okay, it's this value because that's the only one that we've got there. So it's from the left, you have to use the one less than or equal to.
Oh, okay.
The limit as x approaches -1 from the right, that's with the plus there.
Can you use either of them?
No, you have to use this one. So yeah, this one's for bigger than -1. This one's for less than -1. This is, I know it's -1 to 0, but you assume it's the one here. So it is -x, but you're putting the value of -1 in for -x.
So 1.
So it's 1. Okay.
I see.
And then we can sort of answer part B here because it's a continuation of this, which is, does f have a limit as x approaches -1? And the answer is yes, because it's the same value.
Okay.
So it's almost like we need a table here, which is something like left, right, and then an x value. We've kind of already done this for the first one there. So at -1, it approaches 1 and 1, and then is it the same? You know, we can say yes, kind of thing.
Okay.
So we'll now do it for 0. We'll now do it for 0. So we're going to go back up. For 0, I'm going to use a different color here. The different color will be blue. For 0, we're going to use these two. Oops, sorry, we're going to use, let me grab that color again. We're going to use this one and this one.
For what was the value that you're picking?
For 0.
Why wouldn't you use the x equals 0 one?
That's only if it's exactly equal to 0. So limits, you have an approaching value from the left and from the right, but
Okay.
not the same. So we're going to use these for x equals 0. Limit as x approaches 0 from the left. We use this top one because from the left means a little bit less than 0, and that's this part here.
Wouldn't it just be 0 because it's like
Yeah,
-0?
yeah, exactly, which is 0. Then we're going to do the limit as x approaches 0 from the right.
Same thing.
Same thing. It's going to be
So then it does exist because they're equal.
Yeah, so we can come down to our table. It's 0, 0, and yes, they are the same. And then we do the same thing for 1. So we're going to do this a third time for the value of 1, and you just got to grab the right ones here. So the red, I know red isn't the greatest color.
Yeah.
We're going to use it for 1 there. So see how the top one is just a little bit less than 1, and this one on the right is for a little bit bigger than 1.
Right.
You want to do those both. So it's the limit as x approaches 1 from the left, f of x, and that's
The
minus
first one.
Yeah, it's -1 because it's minus x. And then you do the limit as x approaches 1 from the right, f of x, which is 1, this equals 1.
So no.
So they're not the same this time. So that's going to be useful in instead of the other ones. So let's talk about what happens at 1. We can use the table here. We actually need more than this, but maybe I'll revise the table. So I think I said it was -1 and 1. No, they're not the same. Okay, so that answers part A, and then we've got part B. This is part B, is like whether they're the same.
Okay.
Let me try to. So there is a better table here. So let me. Do you have this page in front of you? Like, can you see it?
The textbook, yeah.
Yeah. Okay. So there's the left, there's the right, and these are limits, and then there's the f of x value. So I'm gonna copy these in from the previous tables there. So x is 0, and this I think will really help you to understand limit exists and then continuous. They somehow, the instructors just don't do a good job of stepping you through this. So let me get these values here. 0, 0, 0.
Well, the only thing like I learned about continuous last year was like you don't ever pick up your pencil. It's like the definition.
Right. Okay, so when x is -1, we found the left limit and the right limit, but what is the actual value when x is 1? So go back to your piecewise function, which is in that snip here. And which one do you use for when x is exactly equal to -1? And it's this top one here.
Oh, okay, I see. Well, couldn't it be the bottom one too? Because that could be.
It's only the second one is only defined for less than -1, not exactly equal to it.
Oh, okay.
Okay. Now at 0, it says when x is exactly equal to 0, it's 0. F of 0 is 0.
Isn't it 1? X equals 0.
I'm sorry. Yes, it is 1. Thank you. I misspoke there. And then the last one, when x is 1,
it's 1 also.
It's 1. Okay. So to determine whether the limit exists, you're looking at these two columns and you're asking, are they the same? We already said yes, and the value is 1. Yes, and the value is 0. No. Okay. Continuous, all 3 are the same.
No.
So these are. See how these are all the same?
Oh, I thought you meant like all 3. Okay, yeah. So yes.
And see how these next 2? No, because they're not on the same.
No. Okay.
No. And this is the key. This table summarizes kind of this: does the limit exist, and then is it continuous? So that like you need more to be true for it to be continuous.
Okay.
So I'm going to kind of just break away from this briefly here and show you something that I think will help to clarify this. I just made up this function. This function is continuous everywhere. That means that the limit left and right is the same everywhere. So if it's continuous, you get all this other stuff that's really cool. Like the limits are the same from the left and the right.
Right.
But now let me draw something that is not continuous, like the absolute value function. Okay, so this is continuous everywhere except this point. Do you agree with that?
Mhm.
So when it's not continuous, okay, there's a place where it could be that the limits are the same, but in this case, it's not. Okay, so here's another, let's draw another graph. So these are the ones that are not as good. So let's say it's like that and like that.
Well, isn't it not continuous because it has a removable discontinuity?
This one has a jump, this one has a hole. So the jump can never be filled in, but the hole can be.
So if you're given like a graph like that, like the whole one, and you're asked if it's continuous, you
It's
would say,
continuous everywhere except where that hole is.
okay.
And then there's a third type. So there's 3 types of discontinuities that you need to be aware of. And the third type is a vertical asymptote.
What is how do these look as like equations? Like, how do you know that it's a whole jump or a,
Well, I'm just talking more generally. They're piecewise. That's how you know. They're like this. This is where they generally come from.
but like, if you're given an equation, would they ever ask you to say, is this a whole jump or?
Probably not.
Okay.
What I'm trying to show you, though, is that the hole here is like the example of number 2, where it approaches the same value, but the actual output there is something else.
Right.
Number 1, this first row is like this nice continuous function where everything's good.
Uh-huh.
Okay. And then this last row where it approaches one value from the left, another value from the right is like a jump.
Okay.
So you can see those. Okay. Let's move back to your question. So we got 43 is next, I believe.
Wait, did we finish 29?
I think so.
Oh yeah, we did. Okay.
Yeah. So basically it's all summarized in this table.
Yeah. Okay.
43. Okay. So 43 is on the next page. All right. So average rate of change, you were asking about this yesterday or 2 days ago or 3 days ago
Yeah.
when we met. Average rate of change is slope. It's a fancy word for slope. It is not the derivative. It is slope. It's like algebra 1, algebra 2, pre-calculus stuff. Okay. It's a formula. The average rate of change, though, is f of b minus f of a over b minus a. So f of x is 1 plus sine x. F of 0, which is a, is 1 plus sine 0. So you can't forget your trig. You have to, remember your unit circle values. This is 1.
Oh gosh.
Yeah, not great, but it's okay. 1 plus sine pi over 2 is 1 plus 1 or 2. So in your problem, it's f of pi over 2. That's b. A always comes before b, minus f of 0 over pi over 2 minus 0. We have these values. So there's nothing to do here other than to just put them in. So you got f of pi over 2 is 2 minus 1 over pi over 2. 1 over pi over 2. Whenever you have 1 at the top, you just flip the fraction at the bottom. It becomes 2 over pi.
Okay.
You should be expected to do that. I mean, a reasonable change to make that cosine x, or or maybe change the interval a little bit, but You have to know this formula on the left here. You have to know how to find the slope.
And you have to know the unit circle values
Yes, yes.
that I could learn today.
Yep, something to get on a Sunday. Okay. All right, so 47 is pretty involved here. It's multiple parts. All right, tangent and normal. Okay, find the slope of the curve, an equation of the tangent, an equation of the normal at P. Okay. Okay, so the tangent line is not, the tangent is the instantaneous rate of change. It's not the average rate of change. There's nothing to do with what we did in the previous problem.
Okay.
To find
For average rate of change, it's going to be with sine.
Slope formula.
But like when you're asked to average rate of change, it'll be with like sine and cosine.
No. I'm just saying that's how the instructor could change this problem. Like if you were wondering how you could get this on the test, it could be any function.
Oh.
You could find the average rate of change of a line, a quadratic, square root, anything.
But tangent is always instantaneous.
Yes. Okay. Yes. And you have to make those distinctions pretty early on in this course to be in good shape. So the tangent line comes from the derivative. And f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h.
Okay.
So do you have an f of x?
Yeah.
Okay, so that's your f of x. You have to find f of x plus h. Okay, so that's x plus h squared minus 3 times x plus h. So that's x squared plus 2xh plus h squared minus 3x minus 3h.
Oh wow. Okay.
You want to be really fast at that. Time. I mean, this we talked about a lot when we were doing the SAT prep. Time works against you on these exams. Especially on the AP, and I think that's why your instructor is giving you those time limits. They're trying to say like, this is serious now. You don't get extra time. Like that's, and right or wrong, that is just the way it is. I got my own opinions on that, but doesn't matter. You're going to go to the AP and you're going to have a time limit as well.
Yeah, I mean, I just took the SAT yesterday, so I know.
Yeah.
Okay, so then you can't really simplify that.
Nope. So you got it now. And so you need that for this though. So it's the limit as h goes to 0, and then you grab all this stuff right here.
And then minus x squared minus 3x
over h. Okay. So what happens here is when you distribute the negative, you end up getting cancellations. Yeah.
So the x squareds are going to cancel, and what else?
So anything without an h should cancel.
Yeah. And then you can do the h's. So it's 2x plus h minus 3.
Yep. A lot of writing. It's just part of this. And then you eventually get to that step where you finally put in 0 for h. Okay, so that's your derivative. We did all of this work to find the derivative f prime of x up here. That's that last step there.
Okay.
We are not done. We haven't even done part A, but that is what we've got. So f prime of x equals 2x minus 3. So part A is asking for the slope of the curve at point P. So point P is 1 comma f of 1, and that means that x is 1. That's what that part means. So we take 1 and we put it in here. Okay. So the slope, which is the derivative at a point, is 2x minus 3. We want the slope when x is 1. So we put 1 into that. So if you can remember to do the difference quotient like we did up above and put that value in, that's what it's asking for the slope of the curve.
Okay. That's the slope at t.
At that point, yeah. So the curve x squared minus 3x looks, well, I'm not even gonna draw where it is. It looks something like this. And at that point, it has a slope that looks like that.
Okay.
Minus 1. Okay. An equation of the tangent. Okay, so an equation of the tangent. So the equation of a line, you're going to use this one more often than not in this class. So what does this equation require? It requires a slope, which you just have,
And a
and a
point.
point, which you also have. It's 1 comma f of 1. So the f of 1, you get this from putting x equals 1 into the original.
Mhm.
So that's f of 1 equals 1 squared minus 3 times 1. So your point is 1 comma minus 2.
Okay, so then it's y minus or plus 2 equals -1 x plus -1.
And does it specify the format of the line? Does it say we want it in slope intercept form?
No, it just is an equation of the tangent at p.
So here's a place where you save a little time is you just leave it like that.
Oh, and he told us that we could leave it in point slope form. He doesn't care.
Good. All right. So C is a bit out of scope for this class, but it's a reasonable, it's like a level, another level to this question. The normal at P. So if I go back to the graph, this is the tangent line. This is the normal line. And so there's the tangent.
The tangent line is like touching it basically.
That's
and
right.
the
Remember,
normal is like going through.
yeah. So in geometry, the tangent to a circle, and
Yeah,
then
I remember this. Okay.
that. Okay. So the normal has a relationship to the slope that you found in part A. So the tangent, I'm sorry, the slope normal is equal to the opposite reciprocal of the slope tangent. So we take the negative of the flip of that
Right.
to get that, and you get 1. So now we need the equation of the line. It should say the equation of the normal line, but it's lacking. So it's y minus y1 equals the slope x minus x1. The only thing that's different between this and the previous part is the slope, because
you use the same point.
they go through the same point. You have to.
Oh, right. Okay.
So it feels like it's a lot more, but it's really not.
Okay. Awesome.
I would rework that question on your own at some point today if you have time, and time yourself and see if you can do it, quickly, because that's one of those free response, a lot of parts to it. Yeah.
Yeah, it's a lot of work to just get to part A.
Yes. Okay, so we got 53, 54, and 55. I'm happy to do those. I do think we should do those, but this is a good time to decide because we've got about 15-ish minutes left, maybe 20, somewhere in there, to decide if you also want us to do any of the math Excel. I'm happy to go through these. They're probably good to do.
I think probably just stick with the book and finish these ones because these are like the free response ones that we're going to get.
Yes. Yes. All right.
Plus the math Excel comes from the book anyway, so.
All right, here we go. So 53. All right. Did you get this? Probably is not a calculator problem, but it would be helpful to graph this, but you cannot, I guess. So the domain comes from remembering that you cannot divide by 0.
Mhm.
So when you're trying to figure when is the abs value x squared minus 9, when is that equal to 0? And this
Three.
absolute,
Three.
yeah.
Yeah, 3
And
squared minus 9.
any other Yes, good. You got both of those. So the graph is kind of interesting to look at. It's probably worth looking at. X squared minus 9 goes through 3 and minus 3. And then comes all the way down to 9. We'll assume that's 9. Well, the absolute value of it, all it does is flip it in the when it's negative. So like this part does that.
Oh.
We might need that later on. So the domain is everything except for positive and negative 3. So it's minus infinity to minus 3, union
Union.
minus 3 to 3, union 3 to infinity.
Okay.
All right, write an equation for each vertical asymptote of the graph. So this is not calculus, this is pre-calculus. It's where the absolute value x squared minus 9 equals 0. We already answered that. It's at x equals 3 and minus 3.
What do they mean by write an equation?
These are the equations. So the
Just like okay.
yeah.
Just identifying them. Okay. There are no horizontal asymptotes, are there?
There are not.
How would you know if there was a horizontal asymptote again?
Oh, I'm sorry, there is. I take that back. That was the graph I made was just of the bottom part. This is one of those where its degree of numerator is less than degree of denominator.
Uh-huh.
So that always has a horizontal asymptote of y equals 0 because the numerator is less than the denominator.
Okay.
Oh, so I guess that is y equals 0. Okay, can we move on to part D?
Yeah.
All right, so even, odd, and neither is a pre-calculus step. So if it's even, and this is the first thing you always try, f of minus x equals f of x. So you literally take x in the original and you put in minus x. So the original is x over absolute value x squared minus 9, and you replace all of the x's. So it's negative x squared minus 9, and then you simplify. So the top is minus x, the bottom is x squared minus 9, and you ask yourself, is this the same? Is it the same as this? The answer is no. It has to be exactly the same.
Okay.
Okay, so now the second thing from here, the second thing you try,
Odd,
and it's a continuation of this. It is f of minus x equal to the negative of the original. Now you take your result, you take this result here and you factor out a -1.
Okay.
So it looks like -1 times x over absolute value x squared minus 9. And if this right here is the original, because the -1 is on the outside, then it is. So this in fact is odd.
Okay.
And it's a choice. It's either even, odd, or neither, and they're mutually exclusive. Let me do it this way: even, odd, or neither. So it's you're one or the other. You can't talk about certain things nowadays, but like it's very clear.
Yeah.
All right. Any follow to that or anything else on that one?
No, I think I got that.
Okay. All right, 54, free response here.
Wait, what about the E?
E. Oh, I don't want to do E. Okay, let's do part E. All right, so it actually, I'm going to scroll back up to this part right here. There are 3 types of discontinuities. There's a jump, a hole, and a vertical asymptote. Okay, the only one that's removable is the hole. Okay, so the graph that we're looking at here for this question, which is not this one, the graph that we're looking at for this one, it has only vertical asymptotes. and that's where it's discontinuous. So they kind of lead you through it. This one does not have a hole. That's not a good example of that.
But it's they're all non-removable.
Right. So so the answer to E is x equals 3, x equals -3. They're both vertical asymptotes, and it's not removable.
Okay. Now we can do 54.
Yes. All right. Moving right along here. Okay. All right. So it says, here's a function. They don't give you A. So part C is kind of the most common question that they ask. They're kind of leading you into part C. But normally they just ask you part C. So the limit as x approaches 2 from the left means using this top one. It's from the left. And that may be what was confusing about all the ones we were doing. From the right is this bottom one here.
Okay.
So when it says 2 from the left, you're taking 2 and you're putting it into this function for x. So part A, limit as x approaches 2 from the left f of x, you're taking this value of 2 and you're putting in for x, 2 squared minus a squared times 2. So the common mistake here is to somehow like try to put something in for a instead of x, but you put it in for x.
Okay.
So that's 4 minus 2a squared.
And that's your answer. You just leave it like that.
That's all you can do.
Okay.
The limit as x approaches 2 from the right.
So then it's 4 minus 2 times 2 squared.
2 squared. So that's 4 minus 8.
-4.
This is very important for part C, is you're setting the results from A and B equal. And that's why I said, like, generally they just move to part C because it's like you're supposed to know this, that you have to put the value in from the left and from the right. So you set these equal.
Okay.
4 minus 2a squared equals -4.
So then you subtract 4. And then you get -2a equals -8. Divide by -2. And then so 2.
It's actually 2 answers there. Plus or minus 2.
Okay.
And justify your answers what you just did.
So are both
Yes.
plus
Yes.
and -2 continuous at that point? At 2?
It's continuous at 2 if A is 2 or -2.
Okay.
All right, moving on to 55. 55. It looks like this review is emphasizing a lot of rational polynomials, rational functions. You might want to go back to, there's this section in your pre-calculus book that's like the 8 steps of graphing, and it'll review all the like possible things. You got like vertical asymptotes, horizontal, domain, holes, things like that, and behavior, and so on. Okay, find all zeros of f. So the zeros of a rational function come from setting the numerator equal to 0. So setting x cubed minus 2x squared plus 1 equal to 0.
Okay.
And I know that one of them is x equals 1, but I'm not sure how you would know that. And that's the problem here, because it's a cubic.
Yeah, so like where do you go from there?
Well, you would use synthetic division to reduce it.
Oh God, I need to remember how to do
which seems out of scope. But I mean, if you had a calculator, you could graph it and find them.
Yeah.
-1, -1, -1, 0. So this reduces to x squared minus x minus 1. And this requires quadratic formula.
How did you know that it was to put the one for use the one for synthetic division?
There's two answers. I did just guess, but the other is there's this formula where this is P of X and this is Q of X.
How do you know what number to put in that little like box again?
It's the one that makes it 0, the guess.
Oh,
The guess is what goes there.
okay.
Good. So the bad part here is that you do have to use quadratic formula on this because it does not factor.
Oh, yikes. Okay.
So that's minus b plus or minus the square root b squared minus 4ac all over 2a. So that's minus a minus 1.
Yeah.
Minus 1 squared is 4 times
2 times 1.
All right, so the part inside I did up here, it ends up equaling 5. That's, I guess, okay. So you get 1 plus or minus the square root of 5 over 2. So that's 1/2 plus square root of 5 over 2, 1/2 minus square root of 5 over 2.
Okay. So those are your zeros?
Yes.
Those two and also 1.
And
right?
1, yeah.
Okay.
So part B says find a right-hand behavior model G of X for F. And what that means is it's asking like what terms take over. And what you're looking for is the highest degree terms. So your original function is here. Let me snip that in. There's your original function. So basically as X gets large, that's not important, that's not important, and that's not important. So this becomes X cubed over X squared.
Okay.
So you just cross out all the ones that aren't the highest degree term in both the top and the bottom. And they're saying call that G of X. That's your G of X. This might seem new, but it's like the right way to do what's the horizontal asymptote of this thing.
Oh, okay.
So part C is the limit.
Oh, so that is your right-hand behavior? Just
That's
over, okay.
yeah. So the limit X goes to infinity f of X, and your f of X is up here. It goes to infinity. And the reason is because X cubed is bigger than X squared.
Right, okay.
And then it also asks for the limit.
But if it's greater on the numerator than denominator, it goes to infinity, and then if it's greater on the denominator, it goes to 0, right?
Yes.
Okay.
So the part B is the limit, or not part B, part C, the f of X over G of X. So that's the limit as X goes to infinity, f of X divided by the limit as X goes to infinity, G of X.
Wait, I'm sorry. And then what if they're the same exponent? I mean, the same
So-
power.
So we did that up here in, I want you to see this because you do know how to do this. Let me see if I can find it. Where is it? I was very first problem. Very first problem. It becomes A over B.
Oh, right. It's just the ratio. Okay.
Okay. So this last one, we're up to like part 2 of part C, which is this thing right here.
Uh-huh.
And you just break them apart into the top and the bottom. And we already did the top. The top is infinity. G of X is this thing we came up with here.
Okay.
And we know that because the top is bigger than the bottom, that this also goes to infinity.
So infinity.
Well, no,
Oh.
they cancel out.
Oh, right.
Yes.
So that is your limit as
Yeah.
x approaches infinity, f of x over g of x. Okay.
Yes. Yes.
Wow, that's
Right.
a lot of work. Okay.
Yeah. Okay. That's a good place for us to stop. Pretty sure we got the full time in, and I will send you the notes in the screen recording out shortly within the next like 30, 40 minutes, whenever
Okay,
it
perfect.
loads.
Thank you.
Thanks again. And let me know if you need to meet up in person this week. We can figure it out, or you can continue doing the virtual lessons if you'd like.
Okay, that sounds good. Thank you so much.
You're welcome. Bye now.
Bye.